In this next example, I'm going to ask you to build a circuit that determines if an 8-bit number is identically 0. So why would I do this? Why this kind of specialized thing? Well, it turns out that you often design circuitry depending on what the computer is being asked to do. And I don't think it'll surprise you to learn that you often will check to see if a number is 0. So imagine you're counting down. Imagine if you want to know, should I divide by this thing, is it 0 or not? And I'm willing to bet if you go back and look at all the code you've written, at some point you've checked if some variable is equal to 0. And sometimes it's useful to have highly specialized circuitry that does just one thing very specific that is very common, because you can put that in the overall circuit board in a place that's very efficient, and you can design it in a way that's as efficient as possible, as to always having general purpose circuitry. So let's do this one very specialized circuit, and it's just a good exercise also of turning the crank of working through our 4-step process. So first things first, what is our input-output? That's always the case. I have a single 8-bit binary number, which means I have 8 inputs corresponding to A0 to A7, the bit positions. And I want to know if this number is equal to that number. That is, all of the numbers are 0. So A0 is 0, A1 is 0, and so on and so forth. Okay? So I could write, so one way to do this is I could say, okay, let's write a 1-bit compare for 0. Build that circuit and then wire everything together, because it seems like maybe, well, that's been the trend. We went from a 1-bit compare for equality to a 4-bit compare for equality. We went from a 1-bit adder to a 4-bit adder. And this seems like a lot of inputs, because if I have 8 inputs, how many rows am I going to have in my table? 2 to the power 8, 256. I'm not writing a truth table with 256 entries, and I don't think you should either. But before we try to design the 1-bit compare for 0 and then generalize it, let's think through this truth table for a second. So I know that I have to enumerate every single possible row for all possible inputs. And I know that there are 256 of those. But what do I also know that's going to happen in step 2? I'm going to go through this output column, and what am I going to do? I'm going to find all the places where there's a 1, and I'm going to build a sub-expression using and not, and then I'm going to combine those sub-expressions using ORs. All right, well, let's think through that. Think through any row here that is not 0, 0, 0, 0, 0, 0 to that. What is the value of I going to be? 0. It's not 0. There is one row, and one row only, 0, 0, 0, 0, 0, 0, 0, 0, where there's a 1. So in fact, this isn't nearly as bad as it seems, because every row, and it's the first row, by the way, on top of that, every row after that will have a 0 in the I. I don't have to worry about those rows, because I'm not going to build a sub-expression for them. So in fact, this truth table is incredibly simple. There's only one row that is relevant to us, because all the other rows will come for free because there is a 0 in the I column. Well, once I have this, I've got a pretty easy expression. Let's write it out. Okay? So what is the sub-expression for this? Well, again, we're going to combine all the inputs with a combination of and not. All right, how do I get a 1 when I have 8 zeros? It's not A, and not B, and not C, up to not H. I take the not of everything. If they're all 0, all of those will be 1. And if they're all 1, well then the whole sub-expression will be a 1. And if any one of these is a 1 to begin with, when I not it, it flips to a 0, and they have veto power. The whole thing will evaluate to 0, and that's 255 rows below this. All right, so this turns out to be pretty easy. The sub-expression, which is also the expression because there's only one of them, is just not A, not and not B, and not C up to not H. All right, now we can draw the circuit. I've got my 8 inputs here corresponding to each of the bits of my 8-bit number. I'm going to shove each of them into a NOT gate. You see them lined up right here. And now I've just got to start ANDing them. Now be careful here, AND can only take 2 inputs. Right? You can't shove all of these things into some big fat AND gate. So you got to start pairing them off a little bit. And you can do it in any different way. You can pair these two, these two, these two, these two, and then combine them. It doesn't matter, because as long as they're all coming into the same AND gates, eventually it doesn't matter the order in which you do them. So let me pair them off 2 at a time. So A and B go through their knots. They go into AND. So at this point, I've pairwise AND everything. And now I'm going to do the same thing. I'm going to pairwise AND, pairwise AND. And then, of course, I just need one more at the very end here, and then I'm done. And notice, follow through. Make sure that this logic works for you. Let's say they're all 0 except for this one. Okay, so that G is a 1. Let's walk through the circuitry. That's a 1 coming through. It gets knotted. It gets knotted, so this is a 0 now. So into this AND gate comes a 0. What comes out? I don't even care what H is. If this is a 0, 0 comes out. All right, 0 comes out. 0 comes out. The whole thing is 0. Notice how any one of these flips to 1, it propagates through the entire circuitry, and I get a 0 out. And the only way I get a 1 there is if these are all 0, they all flip to 1, and then I propagate only 1s through the series of okay, so simple little trick is that because the sub-expressions, we only care about a 1 in the output column. If you have a really sparse set of 1s, you in fact don't have to enumerate the entire truth table. Those zeros are eventually going to get kicked out. It's nice to have them there when you have a small number of inputs just so you can see everything, but as your inputs get bigger and bigger, you can be fairly strategic on how you build those truth tables. Good, so that's a simple step. In the last lecture, I'm going to talk about what are called Karnaugh maps, and these are now a slightly different design that allows us to try to reduce the number of gates. Why do I want to reduce the number of gates? Because that reduces the number of transistors, which means I can pack more and more power. And so there's lots of different optimizations. We can talk for months about that. I'm going to just show you one very simple idea to give you some intuition on how some of this circuitry optimization works. All right, we'll pick it up in a few minutes.